Hi friends, and welcome back to the Control Engineering Geek. Throughout this video we are going to use LQR controller for tracking a reference. So before jump into the example, let's see what is LQR. LQR, or simply, is linear quadratic regulator controllers. So for a given system in the state space format, in the continuous time domain, x dot equal ax plus bu, it is required to determine the matrix gain k of the controller so that the control action minimize the some performance index given in this format here, where the q and r are some matrices that are positive or semi-positive definite for the Q and strictly positive definite for R. This performance index is just the accumulated power of the states and the control action for infinity, or infinity horizon. So it's required to find this matrix gain K in the controller U of T, which is a state feedback controller, so that this performance index is minimized, which is subject to the dynamic of the system. So usually LQR, as its name illustrates, is a regulator controller, meaning that it regulates the states of the given system to zero rather than enforce it to track some reference. However, with some simple manipulation of this control action, we can make this LQR track some reference. So, given this example, like we have this state space dynamic system, where A is given in this format, B is given in this format, which is a single input, single output system. We have one output and we don't have any value for the dynamic D. So, as we mentioned, here it is required that the first state of the system to track some reference which is equal to 1 rather than be regulated to 0 or regulate all the state to the 0. So there are 3 states in this system, and it's required to regulate 2 of them and enforce one of the state to track some reference. This example is borrowed from Modern Control Engineering by Ogata, the fourth edition, which is printed in 2002. Okay. To accomplish this desirement or this requirement here, it is required the control law to be in the form of as shown here. So the first state is not regulated. It is being wanted to track this reference R. However, the last 2 states are regulated as the design of the LQR controller. So this transfer function or this control action here can be written in this format as you can see it here, or we can write it in the block diagram as you can see it here. So basically the states that coming out of the dynamic system, 2 of them are just regulated to 0, so it's been fed back to to form the control action. However, the last state or the first state in the system is feeding back and compared with some reference and then multiplied by the gain K. So let's see how we can use the Matlab LQR command to design or to accomplish such control action. So the piece of the Matlab code starts with the define the system dynamic as it is being given in the example. Then the performance in these matrices, which is the Q and R. Here, since we are enforcing the system, the first state of the system to track some reference, so we give more gain for that part of the state, which is the first state. So first state has a gain of 100, whether the other states has a gain of 1 on 1. The control gain is just a small amount, which is 0.01. Design a controller, LQR controller with Matlab, assuming no tracking. So basically we use the command LQR, we give the dynamic of the system, the state and the control matrices, and the matrices of the performance index. This will give us the gain, the optimal gain that minimizes the performance index we saw in the first slide. We extract the very first value of that matrix, or it's a vector, is a vector, and name it K1. Now apply the design LQR for tracking. So first we need to write this dynamic as our state. So it's basically the control action being embedded in the state matrix, and whereas the control matrix for the new control matrix is just the first value of the computed K here, or the matrix control gain matrix here. Define some time domain from 0 to 5 seconds with increment of 0.01 and use the command step, but in step use the new system here, which is the system with the combined control action in the state and the control matrix, whereas the matrix of the output C and D are the same given in the example. Okay, simply plot the result. So we have Y, we have the result X and T here. The T is defined previously, X computed from the step, and boom, we have the result here. So if you can see the result here, the first state is enforced to track the reference, which is 1 here. However, the last two states, X2 and X3, are enforced to regulate to come to 0 like after 3 seconds. This is exactly what was required by the example.